In the middle of the Cold War, the United States Navy was facing a problem that conventional warships were simply not designed to solve. Deep beneath the ocean, Soviet nuclear submarines were becoming faster, quieter, and harder to detect. They could travel at speeds that many surface ships could not match, and they could disappear hundreds of feet below the surface, beyond the reach of much of the technology available to the Navy at the time. So American engineers began looking for something radically different. Instead of building another conventional warship, they explored a design that could almost rise above the ocean itself. The result was the hydrofoil, and one of the most ambitious examples was a vessel known as the USS Pegasus, a ship that could lift its hull out of the water and race across the ocean at extraordinary speed. But there was a problem. The technology worked, it was fast, it was innovative, and yet, in the end, the Navy decided it was not worth keeping. To understand why, we have to go back to the beginning of the Cold War, when speed had become one of the most important advantages a Navy could possess. By the 1962, the United States and the Soviet Union were competing for military and technological superiority across almost every domain. Nuclear weapons were expanding, missile technology was advancing, satellites were changing intelligence gathering, and beneath the surface of the world's oceans, another competition was accelerating. The Soviet Union was developing increasingly capable, nuclear-powered submarines. These submarines could remain underwater for long periods and operate at speeds that posed a serious challenge to American surface forces. Their ability to travel deep beneath the ocean also made them difficult to locate and track. For the Navy, this created a dangerous possibility. A Soviet submarine could potentially follow American ships without being detected, while conventional surface vessels struggled to keep up with it. Even anti-submarine weapons of the era had limitations, because a weapon was of little use if the target could outrun the platform attempting to attack it. The Navy needed speed, and engineers already knew of a technology that offered exactly that. Hydrofoils had existed for decades. The basic idea was remarkably simple. Instead of forcing the entire hull of a boat through the water, engineers could place underwater wings beneath it. As the vessel accelerated, water flowing over those wings generated lift, gradually raising the hull above the surface. Once the hull was lifted clear of the water, much of the drag created by the waves disappeared. The result was a vessel capable of traveling far faster than a conventional boat of similar size. The concept had been demonstrated as early as the beginning of the 20th century, and by the middle of the century, hydrofoil technology had begun finding practical commercial applications. But there was a major limitation. Hydrofoils worked best on relatively calm water. That was not where the Navy expected to use them. A military vessel operating in the open ocean could encounter large waves, rough seas, and constantly changing conditions. A design that performed beautifully on sheltered water could become extremely difficult to control once the ocean became violent. American engineers therefore had to solve a much harder problem. They needed a hydrofoil capable of operating at high speed while remaining stable in rough water. The solution involved a different arrangement of the underwater foils and an advanced control system capable of constantly adjusting the vessel's position. The ship would not simply ride on fixed underwater wings. Its foils had to work dynamically, responding to changing conditions and keeping the hull stable above the waves. That required sophisticated, automatic controls and hydraulic systems. The Navy eventually moved forward with a series of experimental hydrofoil vessels. Among them was the Pegasus, the largest and most ambitious ship in the program. At lower speeds, Pegasus behaved much like a conventional vessel. Its hull remained in the water, allowing it to maneuver normally. But as the ship accelerated, its hydrofoils could be lowered into position beneath the hull. The increasing water pressure generated lift. The hull began to rise, and once enough speed had been reached, much of the ship was lifted clear of the ocean's surface, leaving the underwater foils to carry the vessel forward. The transformation was dramatic. A warship that normally had to push through waves could instead skim above them. Pegasus was powered by a massive propulsion system, producing roughly 14,000 horsepower, and it could reach speeds of around 50 knots, or roughly 91 kilometers per hour. That made it significantly faster than many of the submarines the Navy was trying to counter. There was even an option for additional jet propulsion that could theoretically push the vessel to much higher speeds. But speed was not the only impressive feature. The ship's automatic control system was designed to keep the hydrofoils stable even in rough conditions, allowing Pegasus to operate in waves that would have made the concept seem almost impossible when the program began. On paper, the idea looked promising. A fast surface vessel could patrol coastal waters, respond quickly to threats, and potentially chase down high-speed targets that conventional ships could struggle to catch. But technology does not exist in a vacuum. While the hydrofoil program was being developed, the broader anti-submarine warfare landscape was changing rapidly. Helicopters were becoming increasingly effective at detecting and attacking submarines. They could move independently of the surface ship, search large areas of ocean, and deploy anti-submarine weapons without requiring a fast warship to physically chase a submarine. This changed the strategic value of the hydrofoil. The very problem it had been designed to solve was becoming easier to address through other technologies. And then the Navy had to confront the hydrofoil's disadvantages. The ships were fast, but they were not as robust as conventional combat vessels. Their unusual structure made them more sensitive to damage, and the weight they could carry was limited. That meant there was only so much fuel, equipment, and weaponry that could be placed aboard. For a military vessel, that was a serious compromise. Speed was valuable, but speed alone could not make a ship effective. A conventional warship could carry heavier weapons, more fuel, and more equipment while surviving conditions that could be difficult for a hydrofoil. The hydrofoil also consumed substantial amounts of fuel when operating at high speed. That made it less economical than conventional vessels for many routine missions. And perhaps most importantly, the program had taken years to develop. By the time the ships were finally entering service, the strategic environment that had originally justified them was already changing. The hydrofoil had not failed because it could not do what engineers designed it to do. In many ways, it succeeded spectacularly. It proved that a relatively large military vessel could lift itself above the water and travel at remarkable speeds. The problem was that the Navy was no longer convinced it needed that capability badly enough to justify the cost and limitations. The Pegasus-class hydrofoils ultimately served primarily in coastal patrol roles. 6 vessels were built, and for roughly a decade they operated as an unusual experiment in naval design. They represented a fascinating moment in Cold War engineering, when military planners were willing to explore almost any technology that might provide an advantage over the Soviet Union. But the Cold War eventually ended. In 1991, the Soviet Union dissolved, bringing the decades-long confrontation between Washington and Moscow to an end. The strategic calculations that had helped justify experimental weapons programs were changing, and in 1994, the remaining Pegasus-class hydrofoils were finally decommissioned. The experiment was over. Today, the hydrofoil concept is remembered less as a revolutionary replacement for conventional warships and more as an example of how quickly military technology can become obsolete. The ships were incredibly fast. They were technically impressive. They solved problems that conventional vessels could not easily solve. But they also demonstrated an important lesson in military engineering. A technology does not have to fail technically to fail strategically. Sometimes the machine works exactly as intended. It is the world around the machine that changes. The U.S. Navy had built the hydrofoil to answer a very specific Cold War threat: fast and difficult to detect Soviet submarines. But before the hydrofoil could become the answer, other technologies began providing better ways to find and attack those submarines. The result was a ship that had once represented the future of naval warfare, but ultimately became a dead end in the evolution of the American fleet. The Pegasus may have been born from the race for military superiority, but its legacy is something more complicated. It showed just how far engineers were willing to push the limits of naval design when speed was desperately needed, And it also showed that in military technology, being ahead of your time is not always enough. Sometimes, by the time the future finally arrives, the world has already found another way forward. If you enjoy uncovering the forgotten technology, hidden decisions, and extraordinary stories that shaped our world, subscribe to Nova Reports. We bring you carefully researched documentaries about history, technology, and the moments when the future looked very different from what we know today. Subscribe to Nova Reports and join us for the next story.